Hello everyone and welcome back to another GIS lecture video. And in this lecture video, we're going to extend this idea of standard distance to incorporate a fairly common situation where your distribution might have an orientation to it. And what I mean by orientation is that maybe your data has a larger distribution in one direction than another. Right? Because implicit in this calculation and definition of standard distance, right, is that the distribution is sort of equal in all directions. And it wouldn't take much imagination to think of scenarios where that doesn't hold. Right? Say, for example, you're looking at a data set of the locations of major cities in a geographic area, right? And you might find that it's not even in all directions, right? Maybe it is sort of generating along a river that runs in a specific north-south directionality, right? And so in that case, right, the distribution may be longer in one direction than it is in another. And so we don't have that assumption here that we have with standard distance, right, that the distribution is more or less even in all directions. And so to account for that, we need to break this equation up so that we're measuring the directionality or the orientation of the variation by breaking the x and the y apart into two separate pieces. So we can measure the variation in the x separate from the variation in the y, and we can create, instead of a circle with a radius, right, we can create an ellipse. And then we can use some trigonometry, which is outside of the scope of this course, to rotate that ellipse so that it matches the orientation of the data. Okay, so I'm going to repeat that one more time. Standard distance has this implicit assumption that the variation is more or less uniform in all directions. And it's not a stretch of the imagination to find that the real world doesn't necessarily work that way. That you might have data that is distributed along a different orientation where one direction has more variation than the other. And we can capture that by breaking the standard distance equation apart into its x component and its y component to create, instead of a circle, we can create an ellipse. And then we can use trigonometry to orient that ellipse along the data set. Okay? So again, we're not going to cover the orientation calculations because that's outside of the scope. But what I do want to cover is this idea of how we break this standard distance equation into two pieces. And how we go from standard distance, which is a circle, to this idea of the standard ellipse, right? Because you'll often see it called standard ellipse, right? And again, the idea here is that we're breaking that variation up. So instead of creating a circle with an even radius, we're going to create an ellipse with different measures along the two axes so that we can show when the data has a directional or an orientation to the distribution. Right? But otherwise, the equation is going to look exactly the same. We're just going to break it in half. So for the x, right, the standard distance in the x is going to be that x component, right, where we have x minus x bar, right, we're summing it up, the square difference over n, and we do the same thing in the y, right, again, we're breaking that standard distance equation up, so we're going to sum the y's, right. We've literally just taken that standard distance equation, broken it up along that addition, so that now we have a different standard distance for the x and a different standard distance for the y. So we can now produce an ellipse that measures the distribution in two directions instead of assuming that it's uniform in all directions. And then we can use trigonometry and linear algebra. Right, we can use trig and linear algebra to orient the ellipse along the axis of the data. Right? So that we can go from having something that looks like a circle, right, to something that looks like an ellipse. That is, the data has more variation in the x than the y, and then we can take it a step further and we can rotate that ellipse. Maybe it runs at a 45-degree angle like this, right? So that's the evolution of this measure of variation in geographic distribution, right? We started with the standard distance, which assumed it was a circle and it was a uniform distribution in all directions. We then separate that out into the x component and the y component, which means that we can have a different distribution in the x versus the y. Maybe the data is squashed or stretched in one direction. And then we can take that a step further with the trigonometry or in linear algebra, which we're not going to talk about, to rotate that ellipse to measure the orientation of data where it might not necessarily be in a north-south or an east-west orientation. So hopefully this makes sense, this concept of the standard ellipse and how it extends from this idea of the standard distance, and how we can use standard ellipses to measure not only the sort of variation in the distribution, but by breaking it up into pieces, also measure the orientation. And as always, if you have any questions, please reach out. Thank you.